extrema of functions. Extrema of functions of two or three variables. Definition. Let fxy function be a real valued function. And let a b point be a point in the domain of f. A point AB is called a local or relative maximum point if f a plus h b plus k is smaller than f ab for all h and k, such that 0 is smaller than absolute of h is smaller than delta, and 0 is smaller than absolute of k is smaller than delta, where delta is a sufficiently small positive numbers. Likewise, we say that f has a local minimum at a b point if f a plus h b plus k is bigger than f a b. Note that this definition only says that in some region around a b point, the function will always be smaller or larger than fab. Outside of that region, it is possible for the function to be larger or smaller. If the inequalities in the above definition hold for all points xy in the domain of f, then f has an absolute or global, other name, absolute global maximum or absolute minimum at AB point. Theorem 18. Let f x y be a real valued function such that both fx at AB and fy at AB exist. Then a necessary condition for fxy to have local maximum or minimum at point AB is that fx AB is equal to 0 and fy AB is equal to 0. Note that a point AB where grad f AB is equal to 0 is called that critical point for the function fxy. Note as well that the necessary condition mentioned above is not always sufficient to guarantee that a critical point is a local maximum or minimum. In other words, critical points are viewed as candidates for local extrema, or neither. Theorem 18 tells you that to find relative extrema, you need only examine values of fxy at critical points. What do we do to see if critical points are relative extrema or not? If a critical point is a relative extrema, how do we determine if it is a minimum or a maximum? The following theorems answers these questions. Theorem 19. Suppose that AB is a critical point of fxy, and the second order partial derivatives are continuous. In same region containing AB point. Let D1 is equal to fxx and D2 is equal to determinant fxx, fxy, fyx, fyy. 1. If D1 at point AB is bigger than 0 and D2 at point AB is bigger than 0, then F has a local minimum at AB point. Bigger, local minimum. 2. If D1 at point AB is smaller than 0 and D2 at point AB is bigger than 0, then F has a local maximum at point AB. Is smaller than 0, maximum. Three. If D2 at AB point is not equal to 0, But neither of the above conditions hold. Then AB point is not a local maximum or minimum. In this case, the point AB is called a saddle point. Saddle point. For if the two at point AB is equal to 0, then the test is inconclusive. In other words, no information is obtained. Theorem 18 and Theorem 19 can be extended to apply to functions of 3 or more variables. For a functions of 3 variables, to find the critical points, you have to solve the equations fx is equal to 0, fy is equal to 0, fz is equal to 0 simultaneously. Let point ABC be a critical point of fxyz function, or grad f at point ABC is equal to 0. The three variable version of the second derivative test, let d1 is equal to fxx, d2 is equal to fxx, fxy, fyx, fyy, and d3 is equal to fxx, fxy, fxz, fyx, fyy, fyz, fzx, fzy, fzz. Condition 1. D1 at point ABC is bigger than 0. D2 at point ABC is bigger than 0. D3 at point ABC is bigger than 0, then ABC point is a local minimum point. 2. The one ABC smaller than 0. Smaller this time. And D2 at point ABC is bigger than 0, D3 at point ABC is smaller than 0. This is important. Then ABC point is a local maximum point. Condition 3. D3 at point ABC is not equal to 0, but the conditions given in 1 and 2 are not satisfied, then the function f x y z has not a local extrema. At point ABC. And last condition is for D3 ABC is equal to 0. This test gives no information. Absolute minimums and maximums. Absolute minimums and maximums. In this section, we want to optimize a function. That is, identify the absolute minimum and or absolute maximum of the function on a given region. The extreme value theorem guarantees that f function has an absolute maximum value and an absolute minimum value. The analog of this theorem for a function of two variables follows. Theorem 20. If f(xy) is continuous on a closed bounded set, D in the plane, then f function attains and an absolute max value f AB and an absolute mean value f CD at some points AB and CD point in t. Note that this theorem does not tell us where the absolute maximum minimum will occur. It only tells us that they will exist. Note as well that the absolute max or mean may occur in the interior of the region, or it may occur on the boundary of the region. Here is the process for finding absolute extrema. The process for finding absolute extrema. First step, find all critical points that lie in the region D and determine the function value at each of these points. Second step, find all extrema of the function on boundary. Third step, the largest and smallest values found in the first two steps are the absolute maximum and absolute minimum of the function.